Can you see what I'm saying?
No,
Question
the
one.
question, number 3 is the question I'm stuck, I was
Oh,
stupefied
this one?
on.
Okay.
Yeah.
This one up here?
It's easy, I don't know. I don't know if it's just my decimals I'm getting wrong or what.
Okay, so I'll just write that down because it's going to disappear in a second for me as well. So what's that is that I have a mean of 6 and a standard deviation of 2, and we're being asked to find what percentage of people have, whatever it is, a score between 5 and 9. Right, so that's essentially what that says. Now, what you're going to find out is that when you do, and this happens a lot, won't this be 10, that'll be 12, and these two numbers will be different. Because the way WebAssign does is it creates lots of versions of the same question, right? So I'm doing it for these numbers. Do you want me to just do it with these numbers and you can see if the process right?
Mm-hmm.
Or do you have the numbers that you would use and I can use them if you prefer?
Whatever way.
Okay.
I think I'm just writing the decimal. I think I'm writing the decimal wrong.
Okay, so I'm going to put on my calculator and I'll show you the buttons and we'll see if your decimals is your issue, which it could easily be. So I'm going to have to stop that guy and I'm going to go in here, advanced, basic. Please tell me you're seeing a calculator.
Yes.
Yay, okay. Now in this question, you go second distribution and you go to choice number 2, which is called normal CDF. And then the format is small number first, comma, big number second, 9, comma, and mean, which in this case is 6, and then comma, and then finally standard deviation, which is 2. So that's how you find the area between 5 and 9, or as we would phrase it, the percentage of the data between 5 and 9. And then you just hit enter. And the decimal version is 624. If you were doing it to 3 decimal places, it would be 625, because that digit on the 4 would round up because the next number is 6, and anything 5 or bigger rounds it up. So to 3 decimal places, 0.625. If it was to 2 decimal places, it would be 0.62. Does that look like that's what went wrong? You just rounded off?
It's my decimals.
Okay, so yeah, the simple rule is if you round off to 3 decimal places, look at the 4th one, the 4th decimal place. If it's 5 or more, round the last digit up. If it's 4 or less, leave the last digit alone. That's basically the rounding off rule.
Thank you.
You're welcome.
A couple of questions on the 6-3 homework too, but would it be better if I just wait till the end of class?
I don't know. What question numbers were there? I think it's worthwhile for everybody.
Number 2 and number 16. Okay,
2 is a one-off question, so that one I think it is worth definitely me going over, because you'll only get one shot at that, and I think we'll keep the other one till the end. You know, we can do that on our own.
Okay.
So I'm going to go in and out. Okay, so let's see what we have here. We have a histogram of this data. According to them, that's what the curve of it looks like. I'd argue a little bit. To me, I think the curve should probably be a little bit to the left, but no biggie.
Jonathan?
Yes?
What's a good one? Lucas Allen, right?
I can't hear that last bit. Lucas, it sounded like?
Oh, like her last name is supposed to be Lucas?
Whose last name should be Lucas?
So sorry. I'm muting myself.
Oh, is that question nothing to do with me then?
Yeah, sorry. That was definitely not school related. My bad.
Okay. It could have been worse. You could have been cursing and we'd all be offended. So you didn't do anything too bad. Okay, so histogram, shape, and this nice little plot here. Now, does this histogram indicate normality? So if you look at this histogram, yes, we observe a uniform symmetric distribution. And yes, we observe a bell-shaped symmetric distribution. Well, you don't use the word uniform. Do you know uniform means all of equal height? So I'm picking that one. Now, that's maybe not your question anyway, but since I'm doing it, might as well do it now. Does the normal quartile point, that's this thing, does that indicate that the data is normal, right? So that we can use all the color stuff. And the answer is yes. And yes, the points fall approximately on a straight line, right? Which is the test, right? Now, compute the interquartile range. Very faintly, can you see that the Q3 is 31? And then you take away Q1, which is 27. And that would make the interquartile range 4. You agree? Right. So check for outliers.
Yeah, that's the part I had a problem on, because I thought it looked like there's just one data point, not two data points that are on the boundary. So that's why I selected that there are no outliers.
Okay, now if you're going to do outliers, we can do the upper and lower fence test, or we could do, as they do, the 2.5 standard deviations. It bugs the heck out of me, but we have to do what they do, right? If there was going to be an outlier, would you agree it would have to be at the extreme ends? And the way I'm looking at this data, there's no way that that 34 could be an outlier, right? And there's no way that 27 really should be an outlier. So my answer to that question is there is no outliers. So what was the problem?
That says, I selected there are no outliers too, and I got it wrong.
What does it say there is?
Oh, I didn't put the...
I got that one right.
Yeah, it's the second one.
It's,
I think
It's the
it
second
says
one.
that there's
Yeah.
no
Oh.
outliers, but the data points fall exactly on the boundary.
Oh, moral of that story is read all 4 choices. There was another no there. I just didn't see it. Okay, that makes perfect sense. I don't know about the boundary points.
Yeah,
2
when
data points.
I calculated the upper and lower fence, and
Uh-huh.
only one data point, the 34,
Yeah, but how many 34s are there?
2 it looks like.
That's why.
Oh, I was thinking...
You're thinking
they-
the number 34, but not how many 34s there were.
Yeah, I was thinking 2 data points on the boundaries would be 26 and 34, not...
Yeah, you were looking at the
34s.
start and finish, but no.
Yeah.
Okay.
Oh, okay. That makes sense
Right.
now.
Well, I failed on not reading that one, and you failed on not reading the other one. So that's a 50-50 on that. Are we okay with the rest, or do you want me to? This compute the Pearson's index. You just have to go and look up the textbook and figure out what that thing is. And it'll tell you yes or no. And then your final conclusion based on that. So right now, we finished, I believe we finished at least on finding magic z-scores that would give you an area to the left or to the right. So let me do that as my kind of overlap. That way my brain will be hopefully back into sync. So if I gave you a question, something like this. The mean of a distribution was say 100, and the standard deviation is 10. Do you all recognize my favorite IQ numbers? Right. And I wanted to know what IQ score would give you, and let's do a little picture. What IQ score would give you 5% there? So I guess what IQ score would you need to be in the bottom 5% would be one way of phrasing that, right? Now, if you want to find these, oh, let's rewind. I know I've done that with my evening class. Did I even do that with any of you yesterday? We did. Okay, so this is an overlap. So there's going to be a guy called inverse norm. And the format for inverse norm, at least for the calculator I've got, is 3 numbers. In here, you put that guy. As what numbers do you put into these 2 places?
0 and 1.
Well, that's what you would do if this was a Z-score question. You're right.
Be
But-
100 and then 10.
And 10. Agreed? But
Yeah.
0 and 1 would work if it was find a Z-score that was the bottom 5%, right? So that would certainly be true in that case. Now, in this situation here, then, we simply just plug in this, and I believe there's going to be 2 versions of that. So can I show you? I think I'll be able to do it. Wait a minute, I have to do something else here first. You're just going to have to wait a few seconds. I'm loading up a different emulator. And I'm now going to do a share on my second screen. And if this works, I am going to be so happy. Are you looking at 2 calculators?
Yes, this is another win day for you.
I am on a roll. Right. This is a win day for me. Okay. Now, I'm going to do that inverse norm on this. This would be kind of, this is the emulator program, but it might be what your calculator looks like because you've got an older version, right? And then I'm going to show you what it looks like on this fella here. Okay. I've got somebody needing to get in here. Okay, I'm playing about with Windows here because that is covering up something I want to see. Okay, where the heck am I? Right, so let's go. Second distribution. Oh, make sure it's on. Clear that one out of the way. Second distribution. Now, do you see number 3 inverse norm? Hit enter. Now, the numbers that we've got are 0.05, comma, a mean of 100, comma, and a standard deviation of 10. And that's going to tell me that if you are in the bottom 5% of IQs, you have an IQ of about 83.6 if you round it off.
Mr. Robertson, could you go through the steps again on that
Sure.
inputting information,
Yeah.
please?
No problem. Here goes. Second distribution. Right, so you'll be looking at the screen now. Then move down to choice 3, the one called inverse norm.
Hold on, I'm trying to, my computer just keeps saying syntax. My calculator keeps saying error syntax.
And all you're hitting is second or yellow, whatever color your button is, vars. So you're hitting this button second and this button here vars. Is that what you're hitting?
Now I'm there.
Okay. Now you do the little cursor thing up and down, right? Although you can you can actually type in 3 and it'll do the same job. Excuse me.
Yes, sir. Then I hit enter.
Then we hit enter. And then you type in the decimal value of the area, which is 5%, written as a decimal. Then you put in the mean, which is 100. And then you put in the standard deviation 10. I think you need to put the bracket in. I'll make sure I did. And then enter. And that gives me that the IQ score, so this is a score, not a percentage. The IQ score that you need to be in the bottom 5% is approximately 83.6 when you round it off. Right, let's move over to this one, which is, maybe it doesn't look like it, but this is essentially what your modern version of the TI-84 will look like when you do it. So you do second distribution, and you see it starts off exactly the same with inverse norm. But here you get like a little menu that you type things in. So I'm going to go 0.05.
That's
then-
exactly how mine's is looking.
Okay, so you're going to type in 0.05 where it says area. Mu is the mean, so you're going to type in 100. Sigma is standard deviation, so you're going to type in 10. And I strongly suggest that you just leave this thing as left and then scroll down to the bottom. And when you hit enter, you have to hit it another, and there's the same answer. So they both do it, right? They both give you the IQ score that you would need to get to be in the bottom 5%. So if someone has an IQ about 83, 84, that's where they are in the IQ world.
I have a question about
Yes.
that. I understand how to get that to work and to put in, what buttons to push.
Good.
Can you explain again, just sort of in, pretend that I'm a, person who doesn't know anything about this. What does inverse norm really tell us?
Inverse norm tells you the score that you need. I'll write this down as I'm saying it. It tells you the score that you need. In this case, you need to get a score of 83.6. It tells you the score that you need so that you are in the bottom 5%. So inverse norm gives you the score that you would need, right? The number that you would need in your data to be in the bottom 5% of all your data. So you can imagine you have data and there's thousands and thousands of numbers and you put them in order. What number would you need as a cutoff point so that 5% of the data was less than that number? So that's what it basically allows us to do. It allows us to take a distribution and to just ask little questions to do with breaking it apart and seeing where things live. So let's suppose that the average age of OC students is 35 and that the standard deviation of OC students is 15. Right? And I would like to know what age would you need to be in the bottom, making this number up, 23%. You would also get a version of this question that would be very cryptic. You'd have a little picture and they would go, and they'd point at that and say 23%. That's one of the ways in which that question is done. So I'm trying to find what age I would need to be if I was in the bottom 23%.
Would it be 24%? 24 years old?
I don't know. You might have already done the question for me. It could be. I don't know. Did you type it into the calculator and come up with a number?
Yes, sir. I got 23.9, but I rounded.
Yeah, that makes sense to a whole number at least. That's sheer luck that the percentage and the age were virtually the same. I'll just do it on the calculator that's here. Do you want me to go in and out to show you me hitting the buttons, or can I just say I'm doing it and we can trust it?
I'm here. I'm just listening, but I inputted. I followed the first step you showed me, and I got it.
Oh, you cool. I'm just wondering for the whole class, do you want me to go back in and do it on the screen? Kind of halfway there.
Sure.
You don't?
Yeah.
Okay. Kind of halfway there. Might as well do it now. Okay. Do you want me to do it in the old one or the new one? Because I'm not going to have time to do it to both. You want me to do the calculation on the old TI-84 or in the new version?
I mean, the old one is fine.
Old one is fine. Okay. So on the old one, second distribution, I'll go down to number 3, inverse norm. Now in this story, It was the bottom 23%, so as a decimal, 23 is 0.23. And then we're going to type in a mean, which is 35, and then finishing with a standard deviation of 15. And then I'm going to close this guy off, and I'm looking at, you nailed it, 23.9 or 24 if you round it off to a whole number. Are we good so far? Right, now, let's turn this question on its head a little bit. There are some guys out there, some questions out there, and they look kind of different, and we have to figure out how we're going to solve them. Suppose that the mean of a test was 65, and the standard deviation of the test was 6, right? I would like to know what score in the test to be in the top 10%. Now, up to this point, we've always been looking at the bottom, right? The numbers to the left. If I do a picture of this, which is very helpful, can you imagine that 65 is here, and somewhere over here, there's a score where that chunk in there is 10%, and we're trying to find the missing X, right? What score would you need to be in the top 10%? Now, inverse norm is how it's going to work. Something's going to go there. That's 65, that's never going to change, and that's 6. But the number that goes here is not going to be 0.10. That would be the number you'd plug in if you were being asked to find this guy, right?
So the bottom, that's what you'd be asking for the 10%?
Yeah.
Okay.
So if it was 10%, it'd be this guy, right? But do you notice that the question I'm asking is the top 10%? So there's a little minor change. What decimal goes in here to answer this question? And it's not 10%.
0.90.
And can you explain to the others where you got that? Because it is right.
Let's see. I think that's because the score at 90 per. Trying to think how to explain that.
I think I know what you're trying to explain, so maybe I'll help you out. If this piece is 10%, isn't the other piece 90? So isn't finding that score, the top 10%, the same question as finding the score with 90% to the left of it? And since the calculator inverse norm always gets you the score with a percentage to the left of it, we had to convert this question into that. So see if you want to find the top 82%, oh, that's a bad choice. See if you want to find the top 8%, don't you use 92% in your calculation. If you want the top 30%, don't you do 0.7, right? 70%. So that's the only, I think it's almost cosmetic, isn't it? Because it's almost identical, right? It's inverse norm. The mean's the same, right? That's the same. That's not going to change. That's not going to change. And don't you sometimes have to use the number that they give you, 5%? And sometimes don't you have to do the number that they don't give you? Now, there is a term that is very often used in questions where you talk about percentage to the left. And the term is called percentile. If you've ever done your SAT test, I believe one of the pieces of information they might give you is your percentile. For instance, see if they tell you in your SAT test that you are in the 34th percentile. What does that mean? Well, can you imagine that this represented all the people who took the SAT test. And can you imagine over here is your score? They are telling you that you did better than 34% of the other people, right? So you got a better or equal score to 34% of the people. Isn't there another way of saying that? Which isn't it that 66% of people got a better score than you? Okay. Now, if you're the 90th percentile, doesn't that mean you did really, really good? Because the 90th percentile, right, 90% of the people are to the left of you and only 10 are to the right. Now, I can imagine some universities might use SAT scores in that way. And it goes something like this. We only take people in the 20th percentile into our engineering program. Right? Or we only allow you into our university if your SAT scores are in the 60th percentile or better. Right? So what they're doing there is they're only choosing potential students from using their SAT test is like a wall that you have to climb, right? You have to get a certain grade. Now, I believe in the nursing program, they don't use SATs, but don't they have walls to climb? Like you need a certain GPA, and your wall is that GPA. But can you imagine in a different place where they might have just said, yeah, we've got a nursing program, and we are going to only pick people whose SAT are in the 40th percentile or the 90th percentile. And you see that that is a way of separating people into two groups. So that might be a reason why you would want to do this kind of question, right? As what kind of score did I need to be in the test to be in this particular percentile? I don't think I did this number yet, did I? Right, so let's finish it off. I'll do it over here. Second distribution, guy number 3. You might not see this, but I'm typing it in anyway. 0.9 goes first, a mean is 65, and a standard deviation is 6. And then I'll paste the whole thing, and you're just going to trust me unless you did it. You would need a score of 72.7, so you need a score of about 73. So if you wanted to be in the top 10% of that class, you would need to have got 73 or better. See how that's going to work? Right. Let's do a medical version of this, Stella. Does anybody know, since there are a lot of potential nursing people with us, does anybody know what the typical blood pressure systolic is for a healthy person?
120.
Okay, 120. Now, the next number you probably don't know, and that is the standard deviation. So I'm going to make this up. I'm just saying it's 9.9. Now, that number does exist. And if I had time, do you know, I'd just Google it. And I'd basically Google something like, what is the mean and standard deviation for blood pressure? And somebody somewhere will have written it down, and I'd get that. But can we just pretend this is Scottish people then, right? Now, tell me if I'm right. Is it called hypertension if your blood pressure is too high, right?
Right.
So let's say that in Scotland, that you are only going to be considered in that group if you are in the top 5% of blood pressure. So you can imagine what the blood pressure looks like. Right in the middle is 120, but aren't there some people, you know, getting bigger and some people on the other end is less? And I'm looking for what blood pressure do you need to be considered to have hypertension, right? So what do? We do inverse norm. We only have one question, and that's what decimal goes here, because won't the mean be 120 and the standard deviation will be 0.9? Great. Now the question is, in this story, and that's why I think pictures, for me anyway, pictures are helpful. if you're doing the top 5%, don't you mean this guy over here? And you mean this bit is 5%. But for the inverse norm function, what number do we use in a situation like this? It's very like the IQ one or whatever it was I did before. What goes here?
0.95.
0.95. Right? Now, inverse norm, hit a whole load of buttons to save me jumping in and out and doing my thing over here. Has somebody beat me to it? What would the number have to be for Scottish people to be considered hypertension?
121.5.
Which means that my standard deviation is ridiculously small, right? But can you imagine it was 15 or something, right? That would get you a more accurate result. That is now bugging me. So I'm going to do my next question accurately by using real life data. And to do that, I need to, eventually, I need to find who's the most likely. I'll do Google. So you can't see this, but I'm typing in Google right now. And I'm just going to ask that question. I'm going to ask, what is the mean and standard deviation for blood pressure? And we better get a hit early on. Okay, they are giving me the systolic one. I'm assuming that you gave me the other one, which I can't remember what its name is. So I'm using that one.
I
So,
give you the systolic of 120 and
Okay.
diastolic 80.
huh. Well, oh God. Okay, then I'm going to cheat a little bit. I'm going to use your mean of 120. And they have a standard deviation of 13. It might be, I don't think it is, it might be just a feature of the units that were being used. Right, so I'm going to have to close this fella off. And okay, I've lost you. Okay, you're back. Gotcha. So that's the real number. Okay. What do you call it if you've got really low blood pressure?
Hypotension.
Hypotension? Spelt something like that? Okay.
Yeah, looks good.
Right. Now, let's just say that you're in hypotension if you're in the bottom 10%, right? Let's say that was just an arbitrary cutoff point that doctors have agreed on. Whatever it is, I don't know, but they have a number, right? Now, right in the middle, you can see that it's 120. In this case here, isn't that a little bit easier to do because isn't the number going to be 10%? So let's do an inverse norm. And the mean that we're going to have, well, the number we're going to have is 0.10, which is 10%. The mean is going to be 120, and the standard deviation is 13. Right. Can someone do that quick hit for me and tell me what the number that corresponds to?
103.
Does that look good? Very good, thumbs up. Right, how realistic does that sound? Would a 103 concern you? So can you imagine where they got the magic numbers? Now, I'm assuming that if you're a nurse, they don't go into the details, don't they? Just say anything less than this is hypotension, right? Anything between this number and this number is whatever you call it before your hypotension. And then there's a big chunk in the middle where normal. And then you go the other side, you get hypertension and so on. Do they have a name for the guy that isn't hypotension, but you aren't quite normal, right? You're on the way there, like pre-diabetes. Do they stick the word pre in front of it?
Borderline.
Say again?
Borderline hypertension.
Oh, borderline. So instead of pre, they say borderline, right? So you would stick a borderline. Can you see where these numbers are coming from now? Can you see? Now, I'm saying it's 10%. Maybe you have to be in the bottom 5%, or maybe you have to be in the bottom 15%, right? Somebody somewhere has arbitrarily kind of decided, you know, where to put the goalposts, right? Where to stop to make that decision. So we have got a very powerful technique here, haven't we? That as long as I know it's normal in shape, and I know the mean and standard deviation, can't I find percentage of data bigger than a number, percentage of data less than a number, percentage of data between two numbers? And I can also tell you what score you need to be in the bottom 10, and what score you need to be in the top 15. So if you take take potassium level, couldn't you do a table like this for potassium? And then have a cutoff point. If your potassium level is lower than this, you're in trouble. And they'll probably have some medical name that means you don't have a lot of potassium in you. And then at the other end, there'll be a number and your potassium's too big, and they'll have another different medical name for that. And some of you have done that class. Is it full of Latin and Greek words?
No, it's just hypo and hyperkalemia.
Oh, that's kind of boring. But you know that hypo is a Greek word, it's a Greek root. So there are some Greek words in there. Changing the subject. I'm going to go in for a few minutes and look at the homework that is to do with that, and that way it'll give me a chance to see if I screwed up anywhere. Right, so can you see that this question here is basically back to the early stuff? What percentage of data is between, say, 5 and 9? So won't that just be your normal CDF, guys? Normal CDF. If you want bigger than 120, won't you go 120,999? That's how you do bigger. If you want to do bigger than 2, don't you do 2,999? Now, here is the other version. Find Z such that 5% of it lies to the left. Now, if the picture, would you agree that that one suits 5% to the left? And since this is a normal distribution, won't you do inverse norm? Anyway, you do, even if it wasn't. But won't you do inverse norm 0.05, 0, 1? Because for the standard normal, isn't the mean 0 and the standard deviation is 1? So it's exactly the same question as we've been doing today, but the mean is considered to be 0 all the time, and the standard deviation is 1. So if you see questions that have Z-scores in them, you automatically assume 0 mean, standard deviation 1, right? And you do what you need to do. Here's a Z-score to the left of 74%, so I'm assuming it would be what, that picture? And then you do an inverse norm of 0.74. And that's another similar one. Oh, here's a to the right. Okay. Find a Z-score that's to the right of, well, it's 6%. So I think it'd be this picture. Would that look 6% to the right? Now, if you're doing this one, you do inverse norm. Will you use 6%, 0.06, or will you use the 0.94 in this story?
9.4.
9.4. Can you tell by looking at the question which of the two options is the right one to use in the context of the question? To the right of something as in this case, don't you use the other decimal, right, the 0.94. If it's to the left of something, don't you just use the decimal untouched. So area to the left is 6%, is 0.06. Area to the right is 6%, is 0.94. Do you see, it's the same calculation, right?
So don't mind me asking, like, say with question 6, like up on question 6 and 5 and stuff, is it the same format for like 10 and such?
Question 5 and 6 are not. Question 5 and 6 are the normal CDF questions. Right, so you do normal CDF has little number, comma, big number, comma, mean and standard deviation, right? And those are for finding percentage of data between two numbers or bigger than a number or less. And now
don't mind me asking, could we go over that or do a couple of those, please?
Okay, so let's pick 2 that I can see right now. This would be question 4. I'm writing them down first and then we'll deal with the mechanics of it in a few seconds. And question 5, again, I'm just writing down the data. And okay, so let's close off this fella and go in to here. Right. In question 4, the mean was 15, the standard deviation was 3.4. And we're being asked to find what percentage of the data is between 8 and 12. Do you see that this is not, here's a percentage, find an X, isn't this, here are some X's, find a percentage. It's the kind of the reverse process. Now, if I draw a little picture of this, because it helps me, 15 is in the middle because that's the mean. Wouldn't 8 be somewhere around about here, and wouldn't 12 be somewhere around about here? So I'm basically finding that little piece of the pie. Now, when you have a question that involves finding the percentage of data between two numbers, you're going to use the guy called normal CDF, which I believe is option 2, isn't it, in the calculator? And you do little number, big number, mean, and standard deviation. And that will get you your answer. So I'll quickly do that on my calculator. So setting distribution, choice number 2. You do an 8, a comma, a 12, a comma, a 15, a comma, and a 3.4. And I am looking about 0.169. So 0.169, which I'm going to round, well not round, I'm going to call it 16.9%. Now, this second one, if you imagine the mean is at 106, and you're trying to find what percentage of the data is, say, bigger than 120, you're also going to do a normal CDF in this question. And if I planned ahead, I would have given myself more room. Now, to do things that are bigger than, you go 120 first, and then what magic number do you put as your high number?
999.
Right, you phone the police, right? At least in Britain. So I'm going to go inverse norm that guy again. Not inverse norm, sorry, normal CDF. I'm going to go 120, comma, bigger, which is 999, comma, 106, comma, 17. And the answer I get in this second question, the answer to this fella, is 0.205, which I will convert to 20.5%. So that's how you do those types of questions. Now you notice that the main differences are normal CDF, not inverse norm, normal CDF. You see, normal CDF is when you're being asked to find the percentage when you know a start and finish number or the percentage bigger than some given number. So you're basically finding the area of the piece of cake. In the inverse norm, you know the area of the piece of cake, you're trying to find the number that would make that happen, right? It's a kind of the opposite way around, isn't it? One, you get the percentage and you find the number, and others, you get the number and you find the percent. Did that help?
Yes, sir.
Okay, now I'm going to jump in straight into the second, I think it's the second of the 3 homework sections. So I'm going to have to get totally lost here. And then hopefully I'll get unlost. And this one here is going to be called sampling distribution. And it should kick in. And it is, okay. So I'm going to give you a quick intro to the next section. Oh, darn it, I've lost you. Where are you? Stop sharing. Back in. Right. Are we all on the white screen? Right, we're back to being in the right place. Right. The thing that we're going to look at now is called the sampling distribution. And it's easy to get a little bit caught up with this, so you have to kind of have your thinking cap on here. I want you to imagine I have a population. Right, everybody in America, whatever it is. Now, this particular population, if it's everybody in America, and we're talking about their age. So you can imagine baby just born, right? And I don't know what the oldest American is. Let's say they're 117 or something, right? That would be what it would look like. It would typically be pretty normal in shape. Would you agree that that would be possible? Now, it might be skewed left or skewed right, but it probably is, you know, mound shaped. Doesn't matter. Actually, strangely enough, it doesn't matter. Do you know this can be skewed left or skewed right, and this is still going to be the same result, which is phenomenal. Up to this point in time, see the guys we've been doing here, didn't we have to assume that the data it came from was normally distributed, right? It wasn't skewed left or skewed right or just random, you know, ziggy-zaggy up and down. Because this technique, the normal CDF and the inverse norm, wouldn't work, right? You could put numbers in, but they wouldn't be accurate. We're now going to look at a population that can be anything. It might be skewed, it might not. It could look like the Himalayas, right? It could have 10 bumps in it. Doesn't matter. But what we're going to do is we're going to take a sample of 1,000 people, and we're going to find the mean of that sample. So let me just pretend that the average age of Americans is 35, just for argument's sake, right? And I take 1,000 people at random, right? A good, simple random sample of 1,000 Americans, and I find their average age. Do you expect that this sample will be exactly 35 in realistic terms? No. Would you expect it to be at least close to 35? Yeah. So let's just pretend that it was 34.3. Not perfect, but within shouting distance of the right answer. In fact, isn't that why we get simple random samples? Isn't one simple random sample hopefully going to get us really near to the answer we're looking for? And since we might never know what that answer is, that's our best guy in time. We've done that process. Now the weird stuff. Bill Gates gives me unlimited funds. And he says, do as many samples as you like. So I decide to do a second sample. Now I'm going to put little numbers on that. So that's X bar 1 means the mean of sample 1. And I'm going to call this little 2. And now I find this guy. Now there are 2 parts to this question. Think practical here. Is there any reason in the world that this should be the same number as that? No, because isn't this 1,000 different people? Maybe 1 or 2 by sheer coincidence the same, but pretty much everybody's different. Is there any reason in the world that this one should be 35 either? No. Hopefully dead close to it. Maybe 35.9. Just a random answer. Now, Bill Gates gave me enough money to do this sample 1,000 times. Well, hopefully not me. I just gave somebody money and they did it for me, right? But we got it done. Would you agree that the same arguments I gave before work equally well? Would you expect the 500 to be these numbers? Well, if you do it enough times, you might get lucky, right? But would you agree that it will vary? Every sample. Hopefully, it'll be close to 35. But if you do something 500 times, don't you expect the odd anomaly, where you just unluckily got a little bit more old people than you typically did for the usual sample? That can happen, right? Or a little bit more younger than you would. So can you imagine then that you might get an answer like 27.5? Here is the dilemma that statisticians have. We don't normally have Bill Gates money. Don't we only do one sample? Wouldn't it be nice if we had a way of looking at that sample and putting a kind of error band on it and saying, okay, we got 34.3, but plus or minus this number is where I believe the real answer is. You know, a little like a tolerance level. Wouldn't it be nice if we could do that? And that's actually what we're going to do. It's called the sampling distribution. And what they found is amazing. Can you imagine that all these means represented your data? So can you imagine that what you have here are 500 different numbers, right? Each one represented what one of your samples came up as. If you take this data, right, these 500, and if you take this data and you make a histogram of it, something really remarkable happens. It will be normally distributed. And won't most of the numbers be dead close to 35? So you can imagine a lot of your samples will be 35.1, maybe occasionally a 35 as well. Maybe more than occasional, right? 8 or 10 times that. You won't get that many 36s, right? As an average, right? 1,000 people. Won't get too many 37s, won't get too many 38s, and so on. And can you imagine that what you get then, this is called the sampling distribution. So it's the data that you would get if you could take lots and lots of samples. Now, for the sampling distribution, the following things are true. 1, it will be normal in shape. Even if the population, this is the weird part, maybe counterintuitive. Can you imagine that the population was skewed to the right? Can you imagine? In fact, it probably would be, wouldn't you? You've got a lot more younger people, you've got a lot more older people than you have younger. Can't you only go to 0 and then you don't have you don't have anybody, right? So would you agree there's a lot of room to the left, to the right of 35? Right, you can go up to 90 and 100s, can't you? But in the 35 side, can't you just go down to 0, right? That's the last age that a baby just born today would be. So I'm saying that's normal. I'm thinking about it, and I think it's more likely to be skewed to the right. Would you agree that the population of America is probably skewed to the right because of the distribution of ages? So can you imagine the population looked like this? Where you still have 35, but up here you're getting 117s, right? Even although that's the population, the sampling distribution will be normal. That's what I mean by it's counterintuitive. When you in your gut feeling, wouldn't you think that the sampling distribution should have the same shape as the population? But it doesn't, right? It just doesn't. And that's an amazing fact. It's a good amazing fact, because doesn't that mean then that I can use the mean of one sample and I can answer some cool questions about it? Well, the first thing, it's normal. The second thing is, do you know that the mean of the sampling distribution and I'll call it X bar, do you know it's equal to the mean of the population? Does that make sense that if you did thousands and thousands of samples, wouldn't the average of all of them be darn close to where the population mean is? Now, what you might not be able to predict is the standard deviation of it. And the standard deviation of the sampling distribution, darn it, I'm going to have to call it S, is equal to this fella. It's the standard deviation of the population divided by the square root of n. And that's just magic. It is because it is, right? You just accept it. Now, you might think, why is this much smaller than the population standard deviation? Well, when you do a population standard deviation, isn't it possible to get somebody who's 100 years old? Or older? Can you imagine that would be a pretty rare event, but it could happen, right? It might happen 0.5% of the time, but it could happen. If you took 1,000 people, what's the chances that you managed to get an average age of 100? Would you agree that that is pretty much ain't going to happen? Now, the reason it ain't going to happen is that the distribution, the variation in means is a lot less than the variation of one number from this from the population. So that is kind of telling me that property, right? Isn't it very hard for a mean to be big? Because don't all your numbers have to be big? Isn't it easier for one number to be big? So that's telling me the variation in the two is different. So if you did the variation of the sampling distribution, it might look like that. And if you did underneath it the variation of the population, it would look like that. Do you see? It's basically, it shrinks it.
So the data points on the sampling distribution, those are each of the means of the 500
sample that you took, yes.
Okay, and on the left page, when you did the means divided by 500, that's the formula to find out the mean for the sampling distribution.
Oh, that 500 just meant there were 500 numbers here.
Yeah.
And if I divided that by 500, it would represent this number as well, yes.
Okay, that's the formula you do to find the 35.
Yeah.
The mean of the sampling distribution.
Yes.
Okay.
So you'd add up all 500 of these numbers and you'd divide by 500. And that would be the mean. And that's a funny word, but it's the mean of the means.
Okay.
Right? These are means. And then you add them all up and you find out what the average, what the mean of all the means is. And can you imagine that that would be a really big data set? Because if you do 1,000 people and you do it 500 times, isn't that 500,000 people in your mean?
Do you mean like all of them together add up to
Yeah.
1,000?
Yeah. 1,000 people 500 times is 500,000 people. That's a huge number. Can you see why the sampling distribution should have a mean that's pretty much the population? Because if you're asking 500,000 people, I'd be very surprised if it wasn't exactly 35 or so close to it you can tell the difference. Are we good?
The standard deviation is sigma divided by the square root of n.
Yeah, n represents how many times you did one sample. So in this case, you see the sample size is 1,000. So if I use this as an example, it would be sigma over the square root of 1,000. 1,000 is this fella. It doesn't represent that number there. Right? The n represents what's the sample size for one sample, right? This 500 doesn't have a name, right? And doesn't get used. Because I couldn't have done this 50 times or 4 billion times, right? But each sample is 1,000. So the 1,000 goes here. The n is the sample size for just one sample.
What would you do if you had multiple different samples, but they were different numbers, like different sizes?
The good question is you don't get that. So you don't need to worry about it. And secondly, in the context of these questions, you only get one sample. And we use the properties of the sampling distribution to do the rest. Let me give you an example of me doing that.
Yeah, thanks. I was just going to ask that. If we can see an example of it.
Let's see some numbers attached to that property, right? Let's suppose I wanted to know the average age of OC students, right? And let's suppose that I did a sample of 100, which is a pretty decent size. It's not huge, but it's good, right? And I got that you were 32 years old, right? That was my sample, right? And let's say, and it's a bit artificial, but let's say that I know sigma is 10 because somebody told me, right? I just get told it, right? Now, what I can tell you is that the sampling distribution would look something like this. And its standard deviation would be sigma over the square root of 100. And now I'm regretting that that's 800. Let's make it 20 just so that the numbers don't look all the same. So wouldn't that be 20 over 10? So won't it be 2? So what you are telling me is that if you wanted to draw what the sampling distribution would look like, wouldn't that be my best guesstimate? That 32, because it's the only number I've got to play with, is probably in the middle. And that won't the standard deviation be 2? So won't this guy look something like this? 34, 36, 38, 30, 28, and 26. And what I have just created here is called the sampling distribution.
So all we're trying to find is just the standard deviation.
Yeah, right now, and the mean, but the mean's the data point. So you
right, they give you the mean, and then we're just looking to find the standard deviation in the sample.
Yeah, and then they add a question. So here's my question. From this sampling distribution, we can make certain inferences, just a fancy word for sensible guesses, right? You notice that's 1, 2, 3 standard deviations. I deliberately chose this number, right? 2, 2, 2, 2, 2, 2. Do you know that from here to here, which is 2 standard deviations away from the mean, what percentage of the data is in that range?
95.
95?
95. So do you know I could say something like this? I'm 95% confident that the actual average age of OC students is in the range 28 to 36, which I could rewrite as 32 plus or minus 4. So what that does is, if I just do a sample and I say, well, my best guess is that the average age of OC students is 32, that's good. But isn't it better if I can give you a little tolerance and say, look, I'm 95% confident, right? I'm not 100% sure. I could just have got unlucky and got a bad sample, right? Because you're never going to be absolutely certain in statistics. But I'm 95% confident that my answer is in this range. Now, doesn't that give you a better feeling for where the average age of OC students is? You're not exactly sure because you can't be on a simple sample, but can't you be pretty close to being sure that it's at least in this range? Now, imagine imagine there was 2 people out there and each of them did a sample and they didn't tell you much, but this is what came back. The average was 35 plus or minus 20, and the other one was 35 plus or minus 2. Wouldn't you be happier with this answer than with that answer? Because with this answer, you're saying you're 95% sure that people are somewhere in that range. In this one up here, well, you're still 95% sure, but isn't that a big load of people in that area? I mean, the average age could be 16, couldn't it? Could be 50, could be 52. At least here, can you get the ballpark? It's 33, maybe 36, could be 34 and a half. But you see, this extra number, right, this plus or minus guy that we're tagging on at the end, isn't that a very useful thing to tag on to your estimate? It gives you a kind of idea of what the ballpark figure is. Now, do you know the only thing that affects the plus or minus? Only one thing affects it. The sample size. If you do a sample size of, say, 1,000 people, you're likely to get an answer that looks like this. If you do a sample size of 20 people, you're more likely to get an answer that looks like that. And it comes because isn't that fella, right, times 2, where this comes from? So what we have here is a pretty resilient way of putting a kind of tolerance on our estimates. So we don't just say, well, the average age of OC students is 35, and then just leave it floating. I can say, I'm 95% sure it's 35 plus or minus 2. Back to my little picture here. Suppose I wanted to be almost certain. Wouldn't I do 3 standard deviations away from the mean? Wouldn't I be almost certain that the average age is 26 to 38? Would that make sense? 2 standard deviations, 95% sure the right answer's in there? Isn't 3 standard deviations almost everybody? So I'm almost certain.
So on that equation, could you, I see how you did it, but could you input that in the information in the calculator?
This guy here? No. Well, I guess I'm not really doing it by calculator because it's not an inverse norm question or that. It's basically just using the fact that I know 2 standard deviations either side of the mean is always 95%. So all I did is I took this number, right? And I did 32.
Yeah.
Plus or minus 2 times this number. And that became 32 plus or minus 4. So I really didn't need it's not an inverse norm. I didn't need my calculator to come up with that. We go with this? Right. So I can do another practice at this, a very quick practice at this. Let's suppose that you did a sample of 10,000 people. Now that is a massive sample, right? And for that sample of 10,000 people, you found that the average IQ score, no, let's not do IQ, that you found that the average height was 66 inches, right? And we're going to try and use that data to estimate the average height of Americans. Now, the fact that it is a sample of 10,000, and I'm telling you that sigma is 5, right? Because you just told that. I should be able to come up with a pretty good estimate, right? A range estimate of the exact answer for what the average height of an American is. So let's see what we have. The standard deviation is going to be sigma over the square root of n. So it's going to be, in this case, 5 over the square root of that number, which I've chosen to come out nice. And I believe you get 0.05, right? Now, if I draw, because I'm a visual person, the sampling distribution, right in the middle, you're going to have 66, right? And then this fella, 1, 2, 3, 1, 2, 3. So 66.05, 66.1, 66.15, going backwards, 59.95, 59.9, and 59.85. Now, this is 1, 2, 3 standard deviations trick, right? Let's say I want to be almost certain, right, that I have the average height of Americans. What would that look like? Well, if you want to be almost certain, wouldn't it be 3 standard deviations either side of the mean? Now, as a calculation, that would be the mean plus or minus 3 standard deviations. So that would be 66 plus or minus 3 lots of 0.05. And that would be 66 plus or minus 0.15. Which is where those two numbers come from, 59.85 all the way up to 66.15. Do you notice how close those are to each other? Can you see that the tolerance is but 0.15? What's that? About 1.5 inches, right, at most. So I can predict within 1.5 inches the exact average height of all Americans by only finding the answer to 10,000 of them. Pretty cool. So let's have a look at the early homework questions. By that I mean the next section. And have I got them up? Right. Now, a couple of things you're going to notice. The first thing is there's only 8 questions. And the second thing is you're going to notice that they haven't done yet any of the questions the way I've done them, but that's to come, right? So, which of the following are examples of populations?
People in Colorado?
I would agree.
Students in your school?
I would agree.
Percentage of people who
Nope. Not per se. Yeah. Aren't those 3 things a load of people or a load of things? That's a population. Aren't the other 2 statistics a number associated with a sample or even with a population? Now, a simple random sample of n, measurements from a population, is a subset of the population selected in a manner such that which of the following is true. So do you know this is asking us what a simple random sample is, essentially? Which one of those dots, and maybe there's more than one, represents a feature that a simple random sample has.
The second one?
So every member of the population has an equal chance of being included in the sample. I would agree. Every sample of any given size n from the population has an equal chance of being selected. Now, you haven't seen it phrased that way, but technically speaking, if I was picking a sample of 100, could any sample of 100 be equally likely as any other sample of 100? So, every sample of size n for the population has a proportionally weighted chance of being selected. Nope. Would you agree the third dot isn't random? Some are more likely to be picked than others, right? And that's not a simple random sample. The simplest method of selection is used in creation. Simple random samples are not easy, so I'm throwing that one out because of that. In fact, isn't getting a simple random sample probably the hardest one to do? It's the best one to do, but it's practically speaking, it's the hardest one to actually do right. What about each subset of the population has an equal chance of being included in the sample? I think it's the way they phrase it. Let me take out the word subset. If you're a woman or a man, you're equally likely to get picked. Agreed? Men aren't going to get picked more than women, or women aren't going to get picked more than men.
Well, what if there's a lot more men in the society or in the population? Then aren't men more likely?
I like your answer, in which case I'm about to change my answer and not use it, because what you said made perfect sense to me.
I'm still a little confused why the third one isn't right.
The word proportionally means to me that some samples are more likely to happen, or some samples are created to happen more
But they're
often.
equally likely.
Yeah, equally I like.
Oh, okay.
Proportionally
Okay.
I don't like. It's not a word I would typically use in English,
Okay.
but that's the meaning I'm getting out of that word. It's like reading a lawyer's document, right? Every word is there for a every word is there for a reason. Right. What is it? I've gone through these because there's 8 questions, so we might as well just call them done, right? So if you can remember the answers, great. Right, what is a population parameter? Well, a population parameter is a, which one of them?
Numerical.
Yes, numerical. It's a hard one to say that. Numerical. Descriptive measure of a
Sample?
Population.
of a population.
Wait, no, population, yeah.
So a population parameter, I know the answer has the same as the question, but that's just them being weird to you, right? Give 3 examples of a parameter. Now, there's a little guy here that you probably haven't seen yet. It's P with a little hat on it. That's how you say it, P hat. That's typically the symbol that you use when you ask people, are you in favor of abortion? And 22% say yes. P hat would be 22, right, %. So, so it's not a parameter. On the other hand, P is. P would be the percentage of Americans who are in favor of abortion. That's a population number. Remember, a parameter is a number from the population. A statistic is the same kind of number, but you're getting it from the sample. Right, let's do guys we do know.
Would sigma be one?
Isn't that the standard deviation of a population? So that's
Right.
a parameter. And who's the third one? Because there's one more.
The mean?
Right, and maybe you've forgotten the Greek letter for it, which I can
Mu.
understand. Yeah.
Yeah,
Right.
sorry.
Yeah, no, that's fine. I knew what you meant. Do you know the 3 guys above it? Do you know they're called statistics? And don't you get those numbers by using the sample? And don't those numbers estimate, for want of a better word, the parameter numbers, right? So would my sample mean be a reasonable estimate of the population mean, right? Things like that, right? Now, I have basically answered question 4 because of what I just did up there. So I'll skip by that one. Inference. It's a conclusion, an assumption, or an observation. An inference, Garnet, this is English language for me, because conclusion and assumption are almost the same, but I'm going for assumption, because doesn't conclusion mean you're certain about it? An assumption means that you believe it's true, I'm assuming it's true. The conclusion is you committed the crime, you're going to jail. The assumption is we think you commit the trial, you might not end up in jail after the trial, right? So I'm being lawyer-esque here, but I think assumption suits the situation better. So it's an assumption.
Sorry, the book explains it as conclusion.
Oh God.
Just the.
Tell me why.
I don't even know. It's just the explanation that they put in the book.
I like assumption better, but I mean, it's the English language, and English language has got nuances to it.
If you see the rest of the sentence
Oh,
is based
the rest
on
that
the
makes more sense.
information, so that does make sense.
Okay. If I had bothered to read the rest of the question, then I may have changed my mind.
I
It's
thought
about-
assumption too, and then I
Yeah.
saw that. I'm like, oh,
Okay. So it's a conclusion about the value of a population parameter based on the information from a corresponding sample statistics and the associated probability distribution. Okay, what types of inferences will we make about a population parameter? Well, we can estimate it, I guess. I'm not really sure about the other three. I guess I should do the answer to these because I hate anything to do with English. That's why English was always my bugaboo. Oh, good. I got the others correct, so at least you can check I did those. Testing. Why would testing be okay? Okay, you got X bar, and you're testing to see if it's a good estimate.
I was going to ask that, like, why is it testing out of curiosity?
I'm not convinced. I know why, but it's like when I give an English essay, when I do an English essay and I get back a B, and I thought it was an A, and they tell me it wasn't interesting enough, and I just think, what does that mean, right? So it is what it is, and who knows? This is what the guy who wrote the book believes, and so I am just saying he has a reason, and I'm going for it, right?
Is a probability distribution the same as a sampling distribution? Oh, no. I know what it is now.
Okay,
yeah,
we're good.
Yeah.
These are the answers, which are very distracting, but that's them. So I'm just leaving these guys here for a second. You can get through them. But have you noticed that there's not a calculation in sight here? And it's like me trying to go through reading lawyers' documents. Not my favorite thing to do, especially when assumption and conclusion, and you're trying to nitpick on the context here, which of those two words is a better fit. So that's a reflection of my inability to work well with the English language. I should say that English language is my second language. Scottish is my first language, but they're actually so close together they don't count as a different one. If I was speaking the true Scottish language, I'd be speaking Gaelic. So I'm going to give you a quick lesson. Here is a phrase in Gaelic. I know very few, but here's one. Cud mil fialte. Cud mil fialte. It's just an exaggerated welcome. It translates as 100,000 welcomes. So cud mil just means 100,000. So cud mil fialte is 100,000 welcomes. If I could remember, which I can't, you can do cud mil and then you put the word for goodbye. But that's probably not a nice thing to say. because 100,000 welcomes is good, but 100,000 get out of here is probably not such a nice statement. So I'm not sure if that one's typically used. Since I'm ranting on here a little bit, which I can, and your fault for making me think of Scotland again, and almost everything today makes me think of Scotland, I'm going to show you a problem with names. If you ever get to see a map of Scotland and you look at many of the mountains, especially the mountains, and most of the rivers have been anglicised. In other words, they've got names that people in England would recognise. You know, they're called the Forth and the Clyde and the Calder, and very anglicised names. But most of the mountains still keep their Gaelic names, so they still have their original Gaelic names. And if you ever look at a map of Scotland and you look at hills, you will find that you won't even have a clue on how to say them. The Gaelic language is atrociously bad language to learn. I have a made-up story. Basically, what happened in most European countries is that virtually nobody knew how to read or write. Even many kings didn't know how to read and write. You had scribes. You said to the person, he wrote the letter for you. That letter was sent to the other king. The other king's scribe would read it out to him. That's how you didn't even need to read and write. It was a very, very specialized job. But what happened is that when Christianity came along, they wanted people to be able to, at least in the later years, read the Bible. And so a lot of, there was a big upsurge in the ability to read. Monks, for instance, all had to learn to read, right? Because you had to read your Bible and, you know, recite all the things that you recited when you were a religious person. And you had to read the gospel, right? You had to be able to do things like that. So a lot of people read. And then from there, it transferred to the general population. So what happened very often was that, and it happened in Scotland, is that monks came to Scotland, and at the time we were barbarians, and we worshipped the usual things that people in those days worshipped, you know, sun god, moon god, earth god, wind god, you know, whatever, stick the word god at them, various gods. And we killed people and sacrificed to them. And the monks said, no, that's not a good idea. And what they did is that they took your language and they turned it into an alphabet, and then they created the spellings of your word. And my story is, I think we got a drunk one. I think he came along and says, what's that word? Bin? Okay, I'll stick an H in there. It sounded like there was an H in what you just said. And so that became, by the way, that just means mountain or hill, depends on how big it is. And then the second one, the result is that there is a lot of people's names in Scottish first names. And that's a typical girl's name. It doesn't get pronounced with the letters that you see. Does anybody know who that's a girl's name? Do anybody know who that girl's is?
Mary?
It's Vary. You would probably call him. I guess that would be the anglicised. Now you tell me why MH became a V. So when you read Gaelic, you know, you see two letters together and you try and say both of them, and it doesn't roll off the tongue, right? And then you find out that the sound it makes has got nothing to do with B and nothing to do with H. But when you put them together, it makes a sound. So MH doesn't look like a V, not in my world, right? So can you imagine my problem in coming to America and finding out that there's 12 different spellings of Catherine? Do you want it with a K? Do you want it with a CH? Do you want an IN, finish in, or do you want an INE? And who knows, I'm just making up. But can you imagine how many different ways you get to spell your name? And here's me suffering over trying to not kill your name. Now, Rachel's got a really easy name, and so does Jenna, but not all of you have an easy name for my vocabulary. And since I was not brought up in America, that's why I'm continually apologizing for murdering your name. Because when I look at it, I'm trying to do a Gaelic on it sometimes and thinking, I wonder if that makes a V sound or something. And it probably doesn't. Right, are we good so far about what we've covered in this sampling distribution?
I have a question about the last thing that you were doing, your last whiteboard notes.
Ah, okay. I'm going to bring my whiteboard notes back so that we can all see what your question was. Get that out of the way. I think that was the last 2 pages.
Yeah, that's it. What I am confused about is I don't understand if the standard deviation is 5.
Uh-huh.
I don't understand the 59.95 being next to the 66 on your.
Okay. So see this 5 here? This is the population standard deviation. See this 0.05 here? This is the sampling distributions standard deviation. So these are 2 different standard deviations. This one is where these 0.15s are getting used. So if you look at actual 0.05, there's the mean, 66. If you add 1 standard deviation, which is this number, do you see that you get 66.05? And if you add another one, do you see it goes up to 66.1? And if you add a third 0.05, you get that. And then if you go backwards, do you see I'm just taking away this standard deviation?
But
So,
wouldn't it be instead of 59.5,